Good evening everyone, good evening. I welcome you all again to JEE Enthuse. I hope you all are doing great, having a good time. So people, if I'm perfectly audible and visible to everyone, just let me know fast in the chats. Hello Saima, hi Alex, hello Pranav, hi Sai, hello Aisha, hi Ashwarya, hi Sana, hello Munir, hello Jawaharlal. Yes, absolutely, you can see the elite lectures, absolutely. Welcome back everyone. Hello Harishma, hello Hamul, hello Harshita. I'm doing good. So if I'm perfectly audible and visible to everyone, just let me know fast in the chats. If I'm perfectly audible and visible to everyone, just let me know in the chats. Yes. Alright, so people, as you all must be knowing, tonight we are going to have the sprint session from the general organic chemistry, right? Well, in this session I have come up with around 50 questions from the general organic chemistry. Let's try to solve these 50 questions and let's try to master a few concepts from the general organic chemistry part, right? So before starting the tonight's session, the ones who have just joined in, the ones who are new to the channel, let me quickly introduce myself. Well people, my name is Wassim and I'm your chemistry master teacher writer on this JEE Enthuse channel, right? The ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this JEE Enthuse channel, right? So do like the video, share the video with your friends and do subscribe to the channel as well, okay? What's the difference between nurture and sprint? Well, nurture series was for class 11 students and this sprint session is for the ones who are going to write the JEE in 2022. Basically, in sprint sessions, we only deal with the questions, right? And the concepts which are involved in those questions. Perfect? Okay. Absolutely, Raghav, you can do that. Perfect, guys. So let me know fast in the chats, first of all, if all of you are super duper excited about the tonight's session, right? Let me know fast, people, in the chats if all of you are super duper excited about the tonight's session. Yes, let me know fast in the chats if all of you are super duper excited about the tonight's session. I'm doing good, Abhishek, thank you. All right, people, all right. So let's get going then. Let's get started with the tonight's session with the first question which is going to be on your screen. These are first few basic questions which are on your screen and you are going to arrange them on the basis of their stability order, right? You are going to arrange them on the basis of their stability order. See guys, the concept which is involved in this one, it's very simple. See what that is all about. Whenever you need to compare the stability of charges present on the elements, how do we compare the stability of the charges present on the elements? Let's say I've got two elements, for example carbon and let's say nitrogen. Let's say these are the two elements which I have taken over here. Let's say this carbon is carrying the negative charge, this nitrogen is also carrying the negative charge, right? I need to compare the stability of the negative charge. I need to see where is the negative charge more stable. Whenever you need to compare the stability of the charges present on the elements which belong to the same period, at that point of time you decide on the basis of electronegativity. Carbon and nitrogen, they are the same period elements. I need to compare the stability of the charges present on the elements which belong to the same period. I will be deciding it on the basis of electronegativity. Now remember, negative charge is more stable on more electronegative element. And positive charge is more stable on less electronegative element, right? So this is how you compare the stability of the charges present on the elements which belong to the same period, right? But if you need to compare the stability of the charges present on the elements which belongs to the same group, for example, I've got oxygen, I've got sulfur. Let's say this oxygen is carrying negative charge, sulfur is carrying negative charge. I need to say exactly where is the negative charge more stable. Since this oxygen and sulfur, they belong to the same group, right? Whenever you need to compare the stability of the charges present on the elements which belong to the same group at that point of time, you decide on the basis of volume charge density, right? Volume charge density, it is basically the ratio of charge on the species to the size of the species. Do remember, volume charge density is inversely proportional to stability. Volume charge density is inversely proportional to stability. More the volume charge density, less is going to be the stability. Now have a look. For example, I need to compare the stability of the negative charge on these two elements, right? Negative charge on oxygen and negative charge on sulfur. Now, first of all, oxygen and sulfur, they belong to the same group, and whenever you need to compare the stability of the charges present on the elements which belong to the same group, at that point of time, you decide it on the basis of volume charge density, right? Now have a look, people. Oxygen and sulfur. Where is the size more? Sulfur has got more size. More size means less volume charge density. Less volume charge density means more stability. So negative charge will be more stable on sulfur as compared to that of oxygen over here, right? Perfect. Now let's try to solve the equations which I'll come up with over here. See guys, if you look at the first question, negative charge is present on nitrogen, negative charge on phosphorus, negative charge on arsenic, negative charge on antimony, right? Nitrogen, phosphorus, arsenic, antimony, they are same group elements. They belong to the same group. And in the group, volume charge density plays the role, right? Volume charge density is inversely proportional to size. Volume charge density is inversely proportional to size. Now, where is the size more? So this antimony, it has got the size maximum among all, right? So size is maximum in the last case. So volume charge density is going to be minimum in the last case. Volume charge density is inversely proportional to stability. So negative charge is going to be stable in the last one, followed by this, right? So this is going to be the order. Perfect, guys. Right? Is it clear to everyone? Okay. Now have a look. If you look at the second case, negative charge on oxygen, negative charge on sulfur. Oxygen and sulfur, they are again the same group elements, right? They are again the same group elements, right? So I'll be again considering volume charge density over here. Now if you compare sulfur and oxygen, where is the size more? In case of sulfur, size is more, less will be the volume charge density. Less volume charge density means more stability. So where is the negative charge more stable? In the second case, as simple as that, right? If you look at the next case, single bonded carbon carrying the positive charge, double bonded carbon carrying the positive charge, triple bonded carbon carrying the positive charge. Now, which carbon among these has got the maximum electronegativity? You will say this one has got the maximum S character, this one is maximum electronegative. Positive charge is more stable on less electronegative element. Positive charge is more stable on less electronegative element. So this is going to be the stability order, right? Yes, 1, 2, 3 is going to be the order. If you look at the next one, negative charge on single bonded carbon atom, this is double bonded carbon, this is triple bonded carbon. Which carbon among the underlined ones is more electronegative? You will say this carbon is more electronegative because it's triple bonded, it has got more S character, right? If it is more electronegative, negative charge is more electronegative on negative charge is more stable on more electronegative element. So this is going to be the order of the stabilities, right? As simple as that. I'm sure it's clear to everyone, right, people? Let's move on. Let's see a few more questions based on the same thing. Have a look. Arrange the following on the basis of the stability order again, right? See guys, negative charge present on this carbon, negative charge over here on this carbon, negative charge right here, negative charge right here, okay? Well, if you look at the first one, this carbon, this carbon, this carbon, this carbon and this carbon. If I need to compare their electronegativities, do remember, electronegativity of this carbon is maximum among all the selected carbons, right? Because of maximum angle strain, right? More the angle strain, more is going to be the electronegativity. That's something which every one of you would be knowing, right? So this carbon is more electronegative among all the underlying carbon atoms, among all the selected carbon atoms. Negative charge is more stable on more electronegative element. So this is going to be the stability order of the negative charge, as simple as that, right? If you look at the next case, I'm selecting this carbon, I'm selecting this one, I'm selecting this carbon and this carbon over here, right? Which carbon is more electronegative? I'll say this carbon is more electronegative among all the selected carbon atoms. Positive charge is more stable on less electronegative element. Positive charge is more stable on less electronegative element. So this is going to be the stability order of these positive charges, right? I'm sure it's again clear to everyone. Absolutely, guys. If you look at this question, arrange the following species in the stability order. Again, the similar sort of question. Say, carbon, nitrogen, oxygen and fluorine. They are the same period elements, right? They are the same period elements. So I'll be deciding the stability of these charges on the basis of the electronegativity. Positive charge is more stable on less electronegative element, right? So this is going to be the stability order of these charges, right? This is the stability order of these charges, as simple as that. Carbon carrying negative, nitrogen carrying negative, oxygen negative, fluorine negative. Again, carbon, nitrogen, oxygen and fluorine, same period elements, right? Electronegativity plays a role. Negative charge will be more stable on more electronegative element, right? So this is the stability order of these charges. Perfect. Sulfur carrying negative, chlorine carrying negative. Sulfur and chlorine, same period elements, again electronegativity, right? Sulfur and chlorine, which one is more electronegative? Chlorine is more electronegative, right? So negative charge is more stable on more electronegative element, as simple as that. Oxygen, sulfur, Se and T, they are the same group elements. Volume charge density plays a role. So volume charge density, as you know, is inversely proportional to size, right? More the size, less the volume charge density. This one has got the maximum size among all, right? So it will be having minimum volume charge density. Minimum volume charge density means maximum stability. So negative charge is going to be more maximum stable over here, right? Perfect. I'm sure this again clear to everyone, right, guys? Moving on to one more. Arrange the following according to their stability order, right? Very simple questions. These are the carbocations which are given with. These are the carbanions which I'm given with, right? I need to arrange them on the basis of stability order. Positive charge on this carbon, positive charge on this carbon, over here, right? Perfect. Well, you can decide on the basis of either hyperconjugation or you can decide simply on the basis of inductive effect as well, right? So basically, over here, towards this carbocation, you have got only one plus I showing group. Over here, you have got two plus I showing groups. And in the last one, you have got three plus I showing groups. Plus I, plus I, plus I, right? All the plus effects, they increase the stability of the carbocation. All the plus effects, they increase the stability of the carbocation, right? Where are the plus effects maximum, right? Where is the plus effect maximum? So I'll say last one is going to be maximum stable, followed by this one, followed by this one. Or you can decide it on the basis of hyperconjugation as well. Over here, this is the alpha carbon. So there are three alpha hydrogens stabilizing this carbocation through hyperconjugation through plus H. Similarly, there are 3,3,6 alpha hydrogens. There are 3,3,6,3,9 alpha hydrogens stabilizing this carbocation over here, right? More the alpha hydrogens stabilizing the carbocation, right? More is going to be the stability of the carbocation, as simple as that. Now, similarly, these are all the carbanions, right? Plus effects, they decrease the stability of the carbanion. They decrease the stability of the carbanion. Over here, you have got three plus I showing groups. They will increase the electron density of this carbon to the maximum, right? So the stability of this one is going to be the minimum. So this is going to be the stability order of these carbanions. I'm sure this is clear to everyone again. Right, people? Very simple and basic questions. Moving on to one more. Arrange the following according to their acidic strength. Sorry, it's not acidic strength. It is, just a second. Guys, am I audible? Just check it once. Am I audible? Am I audible? Just let me know. Yeah? Okay. Arrange the following according to their stability orders. This is again the question based on the stability order. This is again the question based on the stability order. Again, you can solve the question by means of hyperconjugation, right? Or you can simply say, this is the carbon carrying the positive charge, this carbon is carrying positive, this carbon is carrying positive, right? Towards this carbon, only there is one electron donating group, right, attached, right? On all the sides, electron density will be coming, right? On two of the sides, electron density will be coming, right? So where is the positive charge being nullified the maximum? I'll say positive charge is nullified the maximum in the second case. So second one is going to be maximum stable, followed by third, followed by first, right? Basically, electron donating groups, what do? Electron donating groups, they increase the stability of the carbocations. As simple as that, right? This is the carbon carrying positive, this is carbon carrying positive, this is carbon carrying positive, right? Over here, nitro, Cn, and F, right? Which one is more electron? All these are electron withdrawing, basically. Nitro group is maximum electron withdrawing. If nitro is maximum electron withdrawing, it will increase the intensity of positive charge to the maximum over here, right? More the positive charge, less the stability. So stability order is going to be this one. As simple as that. Right, people? I'm sure this again perfectly clear to everyone. Moving on to one more. Arrange the following according to their acidic strengths. We need to arrange them on the basis of their acidic strength. So first of all, how do we arrange them on the basis of their acidic strengths? So first of all, I'll be taking H positive out from here. There'll be negative charge on this oxygen. I'll be taking H positive out from here, there'll be negative charge on this oxygen. Now I have made their conjugate bases. Check the stability of the conjugate bases. Where is the conjugate base more stable? Over here, fluorine is attached at the second carbon, and over here it's attached at the third carbon, right? Yes, and you know, fluorine, it shows minus effect, minus I effect, right? So where is the minus I effect going to be more dominating? I'll say in this case, because fluorine is attached to the second carbon. So it is going to decrease this negative charge to the maximum. So I'll say stability of this conjugate base is going to be maximum, right? So where the conjugate base is more stable, that its acid is going to be more acidic. So this is going to be the acidic order, right? Similarly, do one thing. Take H positive out, negative charge over here. Take H positive out, negative charge over here. Take H positive out, negative charge right here. Take H positive out, negative charge over here. You have made the conjugate bases. Now check the stability of the conjugate bases. This carbon is more electronegative than that of this carbon, than that of this one, than that of this one, right? If this is a more electronegative carbon, it is going to stabilize this conjugate base the maximum, right? It's going to stabilize this conjugate base the maximum, right? It's more electronegative, it has got more tendency to pull the electron density towards itself, due to which the intensity of negative charge will be minimum over here among everywhere, right? So I'll say this conjugate base is more stable, so its acid is going to be more stronger, right? So this is going to be the acidic strength again. I'm sure this is again clear to everyone. Okay, arrange the following according to the acidic strength. It's not acidic strength, it's basic strength. Arrange the following as per their basic strength, right? Okay, arrange the following as per their basic strength. See, over here, this is the nitrogen carrying the lone pair, this is the nitrogen carrying the lone pair, right? This nitrogen, it is sp3 hybridized, right? This nitrogen, it's sp2 hybridized, correct? Now people, I'll say over here, S character is more, electronegativity of this nitrogen is more. Perfect. If electronegativity of this nitrogen is more, it is going to hold its lone pair more towards itself. If it is holding its lone pair more towards itself, so where is the lone pair availability more? I'll say lone pair availability is more in the first case, which makes the first one more basic than that of second one, right? Perfect. Again, the simpler one. Similarly, this nitrogen is carrying the lone pair, this nitrogen is carrying the lone pair, right? But over here, there is chlorine attached, and at the same position, there is fluorine attached, right? Okay. Now, people, fluorine being more electron withdrawing, so availability of lone pair over here will be lesser than that of availability of lone pair over here, right? Because fluorine being more electronegative than chlorine, it will pull this electrons towards it will pull the electron density towards itself, or you can say the availability of this lone pair on this nitrogen will be lesser than that of this one, right? So which one is going to be more basic? I'll say first one is going to be more basic, as simple as that. If you look at the other cases, lone pair on nitrogen, lone pair on nitrogen, lone pair on nitrogen, right? This is sp3 hybridized nitrogen, this is sp2, and this is sp. Perfect. So this nitrogen is maximum electronegative compared to all these nitrogen atoms. Wherever nitrogen is maximum electronegative, you will say it has got it has got more tendency to hold its lone pair. So availability of lone pair will be maximum in this case, and wherever availability of lone pair is maximum, that one is only going to be maximum basic, right? So third one is going to be maximum basic, followed by second one, followed by first, right? So this was the order. Which of the following molecules shows resonance? Which of the following molecule shows resonance? If you look at this one, this is pi, this is sigma, and there is a positive charge, right? Right, people? Now have a look. Is the octet of nitrogen complete or incomplete? Nitrogen is forming 4 bonds, its octet is complete. So does the nitrogen have the vacant orbital? Does it have the vacant orbital? It does not have the vacant orbital. Its octet is complete. So for the resonance to happen, it should be pi sigma vacant orbital. Since there is no vacant orbital with nitrogen, so it's not going to show any resonance, right? Or you can say, if resonance happens over here, nitrogen will be forming 5 bonds, which is not possible at all, right? Similarly, if you look at the second one, this is pi, this is sigma. Does phosphorus have the vacant orbital? Yes, it has got the vacant d orbital. So pi sigma vacant orbital, it will show the conjugation, it will show the resonance, right? If you look at all the other 3 cases, this is negative charge, positive, and free radical, right? Yes, people? So basically, this negative charge, it is present in sp2 hybridized orbital. Even this positive charge is present in sp2 hybrid orbital. Even this free radical is present in sp2 hybrid orbital, right? For the resonance to happen, what should have been there? Since these are present in sp2 hybrid orbital, they are present on the same plane, right? They are present on the same plane. Okay. Since this carbon, it has got the p orbital perpendicular to the plane, and over here, over here, if this lone pair was present in the p orbital which was perpendicular, then only there would have been the case of resonance or something like that. But this is present in sp2 hybrid orbital, this is sp2, this is sp2, so they will be present on the plane, right? So resonance won't be possible in this one, neither in this one, nor in this one, right? As simple as that. So 2 is the only case where resonance is possible. Perfect. Look at the next one. Give the correct order of the following, give the correct order of stability. Basically, you are going to arrange them on the basis of stability order. First of all, count the covalent bonds. 1, 2, 3, 4. 4. This one is also having 4 sigma bonds. 4 covalent bonds. This one is having 3 covalent bonds, right? So wherever covalent bonds are minimum, that's going to be least stable. So 3 is going to be the least stable among all. Among 1 and 2, which one is going to be more stable? Among 1 and 2, which one is going to be more stable? Have a look. Over here, positive charge on nitrogen. Over here, there is the positive charge on this nitrogen. Right here, there is negative charge on nitrogen. Over here, there is negative charge on carbon. Negative charge is more stable on more electronegative element. So 1 is maximum stable, followed by 2, followed by 3. This is the order, 1, 2, 3, right? Right, people? Again, the simpler one. Okay, if you look at the next one, which among the following is more stable? I need to compare the stability. Let's have a look over here. So this lone pair on nitrogen, it's in conjugation, right? It's in conjugation. Perfect. If you look at this lone pair, it is simultaneously in conjugation with this pi bond and this pi bond. So this is the case of cross conjugation and this is the case of linear conjugation, or you can say extended conjugation. And you must have heard extent of resonance in cross conjugation is less, and wherever resonance is less, stability is going to be less. So first one is going to be more stable than that of second one, right? If you look at this one, people, have a look. This pi bond, it's simultaneously in conjugation with these two pi bonds, right? So this is the case of cross conjugation. But over here, there is no such case. Over here, there is no such case, right? Okay, so this is basically this pi bond, this pi electron pair, it is simultaneously in conjugation with this pi bond as well as this pi bond. So I must say, this is the case of cross conjugation, and extent of resonance in cross conjugation is less, right? And this is the case of linear conjugation, right? Or you can say extended conjugation. Better term is linear conjugation, right? So it's going to be more stable. Second is more stable than love first, right? Okay. Let's move on to the next one. Among the following, arrange the following in the stability order. Arrange the following in the stability order, right? Now, people, you all must have heard negative charge carrying capacity of oxygen is far, far greater than that of carbon. Or you can say negative charge carrying capacity of negative charge carrying capacity of oxygen is far, far, far greater than the negative charge carrying capacity of carbon. Or you can say negative charge carrying capacity of oxygen is greater than the negative charge carrying capacity of 10 carbon atoms, right? So if negative charge is there on oxygen and negative charge is there on carbon, where is the negative charge more stable? Negative charge is extra stable on oxygen, right? Because oxygen has got more negative charge carrying capacity, right? If you look, people, if you look everywhere, in the second one, there can be resonance due to which negative charge can come on this oxygen. In this one, negative charge can come on nitrogen, right? In this one, negative charge can come on both the oxygen atoms due to resonance, right? Okay. In this one, there is already negative charge on oxygen, right? It can participate in the resonance due to which it will be having resonating structures, right? Now, people, have a look. If you look at this option D. So basically, in this particular case, negative charge is being shared on two oxygen atoms, right? And we know negative charge carrying capacity of oxygen is far, far greater than that of carbon atoms, right? So D is going to be the maximum stable among all. D is going to be maximum stable among all. Now, right here, you have got negative charge coming on oxygen. Right here, there is negative charge coming on oxygen. So I won't be deciding on the basis of negative charge carrying capacity of oxygen, because over here, negative charge is coming on oxygen, and over here, already negative charge is there on oxygen. Now, you'll be deciding among these two, you'll be deciding on the basis of number of resonating structures. Number of resonating structures will be more in E followed by B, right? So this one is gone, this one is gone, and this one is gone. Now, which order are left? A, C, and F, right? See. Over here, due to resonance, negative charge is coming on nitrogen, more electronegative element. Negative charge is more stable on more electronegative element. So C will be more stable than that of your A and F. Now, among A and F, since the resonating structures are more in F, so F being more stable, followed by A. This is going to be the stability order. D, E, B, C, F, A, right? This is the stability order. I'm sure this is clear to everyone, right? Perfect. Now, people, let's see one more. Compare the acidic strength of hydrogens. You need to see where is the hydrogen more acidic. Where is the hydrogen? Which hydrogen is more acidic? See, if H positive is lost over here, negative charge comes here. Take the H positive out, negative charge comes on sulfur. Take the H positive out, negative charge here. Take the H positive out, negative charge on this nitrogen, right? Now this negative charge on oxygen, it can participate in the resonance, right? Due to which negative charge can come on two oxygen atoms, right? Yes, right? So over here, negative charge is more stable because it's coming on two oxygen atoms. Perfect. So this hydrogen is going to be maximum acidic. This hydrogen is going to be maximum acidic, followed by, if you compare these two, negative charge on oxygen, negative charge on sulfur, right? Oxygen and sulfur, they belong to same group. Volume charge density plays a role. More the size, less the volume charge density, more the stability. So S negative charge on sulfur is going to be more stable than that of negative charge on oxygen. So it is going to lose this hydrogen easily as H positive. So third hydrogen is going to be more acidic, right? Now among these two, if you compare oxygen and nitrogen, they belong to same period, right? Electronegativity plays a role, right? Negative charge on this nitrogen, negative charge on oxygen. Negative charge is more stable on more electronegative element, that is oxygen. So second hydrogen is going to be more stable than that of first one, right? So this is going to be the stability order 4, 3, 2, 1, right? I mean, this is going to be the order of the acidic hydrogens. Perfect. Arrange the following on the basis of Kb, right? So basically you need to arrange them on the basis of their basic strength. See, first one is going to be maximum. It is the famous base, right? Gonadine, right? It is basically going to be maximum basic. It is maximum basic among all, right? Now have a look. See, select the same reference first of all. Select the reference. I'm selecting the reference everywhere. I've selected the reference. Now this OH, it's going to show what? It's going to show plus M effect, right? Right? This CH3, it's going to show plus I effect. Right, this Cn, what does it show? It shows minus M effect, right? So what is going to happen over here? Can I say plus effects, they increase the basic strength, right? So first one is maximum basic, followed by second, right? Followed by third, and followed by fourth, right? So this one is done. Perfect. So 1, 2, 3, 4 is going to be the order, right people? 1, 2, 3, 4 is going to be the order because you know, plus M effects, they increase the basic strength, right? Plus effects, they increase the basic strength. And plus M dominates over plus H dominates over plus I. That's something which every one of you will be knowing, I'm sure. Okay, identify the molecules, whether they are aromatic, anti-aromatic or non-aromatic. Have a look, people. If you look at the first one, there are 4 pi electrons involved in the cyclic conjugation, right? 4 pi electrons, so it's going to be anti-aromatic. Right? 2, 4 and 6. 6 pi electrons involved in the complete cyclic conjugation, so it's going to be aromatic, right? So this carbon is sp3 hybridized, so it's going to be non-planar, so it's going to be non-aromatic, right? Even this is sp3, this is sp3, so non-aromatic, right? Non-planar. Okay. Now we will have a look. What about this one? Well, I can make it like this as well. Have a look. I can make it like this as well. If you talk about this compound in particular, it has got 6 pi electrons. This one is aromatic. If you talk about this one in particular, this is 2, 2, 4, anti-aromatic. So this one is aromatic, this one is anti-aromatic, right? Aromatic plus anti-aromatic makes it anti-aromatic. So the molecule overall is anti-aromatic over here, right? Yes? Yes, all these are basically PYQs, previous year questions. Okay. Identify the molecules, whether they are aromatic, non-aromatic or what. Have a look, people. See, first of all, sulfur has got 2 lone pairs, out of which 1 lone pair will be participating in the complete cyclic conjugation. So 2, 4 and 6. So there are 6 pi electrons involved in the complete cyclic conjugation. If you look at this one, this nitrogen has got the lone pair and this lone pair is involved in the complete cyclic conjugation. 2, 4, 6, 8 and 10. There are 10 pi electrons, right? 6 pi electrons means aromatic. Right? 10 pi electrons, that means it's following the Huckel's rule, 4 to the 8 to 10, right? It's again aromatic, right? If you look at this one, this carbon is sp3, so it's non-aromatic, right? This is sp3 non-planar, so this is non-aromatic, right? So this is how you represent it, as simple as that. Yeah? Okay? Alright, arrange the following according to the stability order. Again, the simplest sort of question again. These are carbocations first of all, right? So this carbocation is stabilized by 3 alpha hydrogens, right? This carbocation is stabilized by 2 alpha hydrogens, right? More the alpha hydrogens, more the plus H, right? More the plus H. So basically, more the alpha hydrogens means more is going to be the stability of carbocation, right? So where are the alpha hydrogens maximum? In 2, alpha hydrogens are maximum, so more stable than that of 3, than that of 1, right? 2, 3, 1 is going to be the order. If you look at the next one, right? If you look at the next one, this carbon carries a positive charge, so it will be having only one alpha hydrogen, right? That is this one. Perfect. There is hydrogen attached. This is alpha hydrogen. Similarly, how many alpha hydrogens? With how many alpha hydrogens this carbocation is being stabilized? This is one alpha hydrogens, and these are two alpha hydrogens. So basically, there are 3 alpha hydrogens stabilizing this positive charge on carbon. Over here, there are 3 hydrogens. Over here, 2. Over here, 2. 3 to 5 to 7. There are 7 alpha hydrogens stabilizing this positive charge, stabilizing this carbocation. Where are the alpha hydrogens maximum? In the third one, wherever alpha hydrogens, the maximum stability of carbocation is going to be maximum in that case. So 3 to 1 is going to be the order, right? 3 to 1 is going to be the stability order. Again, the simpler one this was, right? Okay, arrange the following according to their KB value. So basically, you need to arrange them on the basis of their basic strength, right? As I told you, plus effects, they increase the basic strength. And plus M dominates over plus H, and plus H dominates over plus I. You guys will be knowing. First of all, I'll be selecting the reference. This is the reference, which is common to everyone, right? So there is CH3 attached at the para position. This CH3 is going to show the plus H effect. CCl3 attached at the para position, so it is going to show the minus H effect, right? CH3 attached at the meta position. At meta position, hyperconjugation is not going to happen over here, so it will simply show plus I effect, right? This CCl3 at the meta position, it will show minus I effect, right? So which one is going to be maximum basic? Which one is going to be maximum basic, right? Plus H, plus I. Plus H dominates over plus I. So first one is maximum basic, followed by third, right? Now among CCl3 and among second and fourth, which one is going to be more basic? This is minus H, this is minus I, right? So this one, fourth one is going to be more basic, then comes the second one. So 1, 3, 4, 2 is going to be the basic strength, right? This is going to be the order, right? 1, 3, 4, 2 is going to be the order. Okay, one more. Identify the following as chain or position isomers. You need to arrange them on the basis of, you need to see whether they are chain or position isomers. That's a simple rule by means of which you check whether the isomers are chain or position. That is CS rule, right? That is a CS rule. Okay. Perfect. C stands for the number of carbon atoms in the parent chain. Number of carbon atoms in the parent chain. Right? S stands for number of substituents. Number of substituents starting with carbon. Starting with C. Right? Now, first of all, if you look at the parent chain, 1, 2, 3, 4, 5, 6. So C value is 6. Number of carbon atoms in the parent chain is 6, right? How many substituents are there? 1. And is that substituent starting with carbon? Yes. So 61 is the CS value. 61 is the CS value, right? Now, what about the CS value of this one? 1, 2, 3, 4, 5, 6, right? So there are 6 carbon atoms in the parent chain. There is one substituent, that too starting with carbon. So CS value is coming out to be same. When CS value comes out to be same, are these going to be the position isomers or chain isomers? Let me know fast. CS value same, position or chain? I'm asking you. Till then, I can have some water. When CS value comes out to be same, CS value is coming out to be same, that means these are going to be the position isomers, right? These are going to be the position isomers. When CS value comes out to be different, these are going to be the chain isomers. Have a look. Have a look, guys. If I need to calculate CS value for these two, I'll be starting from here. For example, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 carbon atoms in the parent chain. How many substituents are there? 1 and 2. Both the substituents are starting with the carbon, so 82 is the value of CS. Now check here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So C value is 10 and there is no substituent starting with carbon. So CS value is coming out to be 100. CS value comes out to be different. So these are going to be the chain isomers. When CS value comes out to be different, these are going to be the chain isomers, right? Perfect. Similarly, guys, let's talk about few more. Okay. Draw the tautomers of the following. You need to draw the tautomers of the following. Can you draw the tautomer of the first one? This is C double bond O. This is C double bond O, right? This is the carbon which is attached with the C double bond O. This is the carbon which is attached with the carbonyl group. So in order to show the tautomerism, it should have the alpha hydrogen. It should be sp3 hybridized and it should have the alpha hydrogen, right? It is sp2, so it's not going to show tautomerism. First one, right? What about the second one, guys? This is C double bond O, right? This is C double bond O, carbonyl group, right? If you talk about this carbon, this is sp3 and at the same time, it contains the alpha hydrogens. It contains the alpha hydrogens. So what you need to do, what is going to be, it's tautomer. It's going to be CH2, it's going to be double bond C with this OH and this H, right? This is the enol form, this was the keto form. Right, people? Now have a look over here. We need to draw the tautomer of this as well. See, this is your reference C double bond O, carbonyl. This is the carbon attached with the carbonyl group, right? So it must be sp3 containing alpha hydrogen. It's sp2, right? So it's not going to show. What about this one? This is the C double bond O group. This is the carbon attached with C double bond O group, right? Now people, it is sp3 as well as it has got the alpha hydrogen. So what is going to be its tautomer? It's going to be pH. This is C. This is OH over here. This is double bond and this is going to be its enol form, right? Yes? So I'm sure it's clear. So these are basically the tautomers of the respective. Draw the most stable and least stable form of the following. Okay, if I need to draw the most stable form, I will be looking at this molecule along this way. If I choose this as a line of sight, I'll be looking at this molecule along this way. That carbon which will be visible to me, I'll be representing that with a dot. With this carbon, there are three things attached, chlorine and two hydrogen. Let's say this is your chlorine. Now put two hydrogens over here at an angle of around 60, right? This carbon is something which you cannot see by your eyes, right? That carbon which you cannot see, that's something which I'll be representing by circle. Now it has got chlorine and two hydrogens, right? If I put one chlorine over here, one hydrogen over here, one hydrogen over here, right? This is one of the conformations. This is one of the conformations. What is the dihedral angle over here? What is the dihedral angle? It's 60 degree. Dihedral angle is 60 degree. So is it staggered? Absolutely it's staggered. And in the staggered one, which one is it? Is it NT form? Right? This is the staggered one. Dihedral angle is what? It's 60. So it's going to be maximum stable, right? Which one is the minimum stable among all, right? Which one is going to be the minimum stable configuration, conformation of this one? What I'll be doing exactly? I'll be rotating this circle 180 degree. If I rotate this circle 180 degree, this chlorine will come exactly on the top, right? Okay. That is going to be the eclipse form, which is going to be its least stable, right? If I rotate this circle 180 degree, right? This chlorine will come at the top, right? There'll be two same groups on the same side, right? Which is going to be completely eclipsed. If it is completely eclipsed at that point of time, that's going to be the least stable among all, right? So this is NT form, staggered. This is fully eclipsed, right? Fully eclipsed is the least stable. This is the maximum stable, right? I'm sure it's clear. Okay, draw the most stable form of the following, right? So you need to draw its most stable form. So first of all, I'll be looking at this molecule through this line of sight, right? This nitrogen is something I can see. Nitrogen is something I can see, right? I'm plotting nitrogen over here. It has got a lone pair, right? It has got a lone pair. This is a lone pair, right? And it's got two hydrogens. This one hydrogen attached. This one more hydrogen attached. This carbon I cannot see by my eyes. I'll be representing it with a circle. So this is the circle with which I'm representing this carbon. Towards this carbon, there's a bulky group attached and two hydrogens, right? This is one of the hydrogen. This is one of the hydrogen, right? And you guys know bulky group, if I attached it at the gauge position, it's going to be the maximum stable, right? So this one is the maximum stable conformer of this, right? Perfect. Right, people? Okay, look at the next one. Draw the most stable form of the following by using gauge effect. Again, people, are the same. If I look at this molecule in this way, this is my line of sight. This oxygen is something which I can see. So this is oxygen. With this oxygen, you have got two lone pairs attached. This is one lone pair. This one lone pair attached over here. And there is CH3 group as well. This is CH3, right? This carbon is something which you cannot see. That carbon which you cannot see is something which I'll be drawing by a circle. So I've drawn it by a circle. So towards this carbon, there is a bulky group attached, CH3. And there are two hydrogens attached as well, right? Yes. Now you need to place this bulky group. So where will I be placing it? I'll be placing this bulky group over here, right? And this is going to be H. This is going to be H. As simple as that. Perfect? Right, people? Okay, so that was the most stable form. Alright, one more. Which of the following can show geometrical isomerism? You need to see which one of the following can show geometrical isomerism. For the geometrical isomerism to happen, three conditions molecule must satisfy. If you select two centers, between two centers there should be restricted rotation. Rotation should be restricted, right? Towards this atom, there should be two different groups attached. Towards this atom, there should be two different groups attached, right? At the same time, these two bonds and these two bonds, they should be these terminal bonds. This one, this one, this one, and this one. These terminal bonds, they should be either present on the same plane, or the plane containing these two bonds and the plane containing these two bonds, they must be parallel, right? That's the condition for the GI to happen, right? If you look at the first one, if I select this center and this center, no doubt restriction is rotated, but two same groups attached, right? So it's not going to show GI, right? If you look at the next one, select these two centers, this one and this one, right? There is hydrogen attached, this is hydrogen, this is your CH3, this is your CH3. Restriction is rotated, number one. This is sp3, this is sp3. So the plane containing these two bonds and the plane containing these two bonds, they'll be parallel. So second condition is also satisfied. Third condition, this is CH3, this is H. Two different groups attached with this carbon. Similarly, two different groups attached with this carbon. So it's going to show GI. It's going to show GI, right? What about the third one? If you select these two centers, there is hydrogen attached, right? Restriction is rotated, right? The plane containing these two bonds and the plane containing these two bonds, they are parallel, right? At the same time, one more thing is there. What is that? Hydrogen and this group, different groups, two different groups attached, right? So this is going to show GI, right? What about this one? If I select this center and this center, there are two hydrogens attached with this carbon, two same groups, so no GI at all, right? What about the next one, people? What about the next one? If you select nitrogen and this carbon has got one hydrogen attached with it as well. So two different groups. At the same time, this nitrogen will be having a lone pair, and lone pair is considered as a group, right? Lone pair is considered as a group. So two different groups over here, two different groups over here, right? Again, it's going to show GI. What about this one? Will it show GI? Hydrogen as well as hydrogen. Two different groups, so it's going to show GI. If you select this center and this center, two same groups, it is not going to show GI, right? And last one, it is going to show GI, right? Perfectly clear? Perfectly clear, guys? Yes? I'm sure it's clear to everyone. So these were the questions, people, which I had come up with. Let me see if I have more. No, that was all. I'm sure a lot of things would have got revised from the general organic chemistry part. And if you have not enrolled yourself into the JEE 2022 crash course batch, do it tonight because the offer is valid till 12, right? Okay, the crash course JEE 2022 batch I'm talking about, the offer is valid only till 12. Okay, in just 8K, you're getting enrolled into the JEE 2022 crash course batch, wherein your whole syllabus of your physics, chemistry and biology, your maths will be done, right? And by the best teachers of Vedantu on the actual Vedantu platform. No need to worry about the assignments, no need to worry about the test series, no need to worry about the study material. Every single thing is provided in this particular crash course. But the offer is valid only 10-12, right? Only in 8K you are getting this complete crash course, my dear people. So use this coupon code, right? And get enrolled into this crash course only in just 8K. So how to get enrolled exactly in this crash course which I'm talking about for the ones who are going to write the JEE in 2022, right? That means this year. You need to click on this show more of this video. Click on this JEE crash course. Once you click on the JEE crash course, you need to drag the video a little down. After dragging a little down, click on buy now and give your number, email ID on which you'll be getting the OTP and everything, and eventually you'll be getting enrolled into the JEE 2022 crash course batch, which is there on the actual Vedantu platform, which started today, right? So do get enrolled in it as soon as possible. The best teachers of Vedantu are training you in that batch in physics, chemistry as well as maths, right? Who have got the teaching experience of more than 15 years, right? Study material, every single thing, whatever things are needed for the competitive examination like JEE to get cracked, all those things are basically included in this one, right? So do get enrolled in this crash course as soon as possible. I think this much is enough for today, people. I'm sure you would have enjoyed it, right? I'll see you guys tomorrow with the 13th mock test of your JEE 2022, right? So with this, I'm going to take a leave. Yes. So I'll see you guys tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye. Yes, Tejashwini, that's okay. That's completely okay.